Hi, everyone. So welcome to the Control Meets Learning seminar. So today we are delighted to have Professor Melanie Zeilinger from ETH Zurich. So Melanie is a leading expert in learning-based control, especially on safety-critical systems, distributed control, and optimization. So she's an assistant professor in the Department of Mechanical and Process Engineering at ETH Zurich, where she leads the Intelligent Control System group. So previously, she received her bachelor degree from University of Stuttgart, Germany in 2006, PhD degree with honors in electrical engineering from ETH Zurich in 2011. So she was postdoc fellows at EPFL, Max Planck Institute for Intelligent Systems, and Berkeley until 2015. So from 2018 and 2019, she was also a professor at the University of Freiburg, Germany. So her research has received many awards, including the ETH Medal for her PhD thesis, a Marie Curie IO Fellowship, and an SNF professorship grants. So she is also one of the organizers of the Great New Conference on Learning for Dynamics and Control, L4DC. So today we are delighted to hear an interesting connection between machine learning and model predictive control. So without further introduction, Melanie, the floor is yours.
Thank you so much for the kind introduction. I'd really like to thank the organizers for initiating this wonderful new seminar series. So it's been a fantastic sequence of talks so far, and it's my particular pleasure and honor that I have the opportunity to speak today. So I'm going to give you sort of my perspective on how control can meet learning. And I'll be here coming more from a controls perspective. And in particular, discuss how I think control theory can help us address the challenge of safety when we're looking at learning-based control methods. The things that I'll be presenting have our joint work with Lukas Heving, Kim Babersich, and Andrea Caron from my group at ETH. So let me begin by stating of the problem setting that we're interested in. And I'd like to start usually with a picture like that, just to illustrate the variety of different areas where automatic control is actually important. And applications really range from power systems, manufacturing, robotics, also to medical devices. So what we're interested in is the control of a physical dynamical system. A dynamical system has some internal state, and that internal state is directly affected by the actions that we're taking. So for the purpose of this talk, I'll be using such a discrete time representation of a dynamical system. So we represent the state at the next discrete time step as a function of our previous state, the input that we're choosing, the potential uncertainties or noise and parameters. Now, there's been a clear trend in automatic control towards using learning techniques, and this is really motivated by the fact that these systems can now sense a lot more. They can share information, generate information. They're really becoming one of the largest data generators, and that it offers a new opportunity for their operation. Now, however, it's also clear that this setting of a dynamical system is actually a quite challenging one for learning. And there's a number of challenges that have to be addressed. So I'll first be talking a little bit more about the challenges, and then how we could approach them. People are currently tackling this from both a control or a reinforcement learning perspective. And we'll also be looking at how we can best combine these things. Okay, so while you could just learn in simulation, many of your important effects that you want to learn in order to improve the performance for a particular problem instance, they can only be seen from the real data. And this is because they're due to disturbances. There's a certain interaction here, for example, with the ground. There's variability in your system. So the setting that we want to focus on is that we really have to learn during operation of the real system. And that leads to a number of distinct difficulties that I think are also quite at the heart of why these techniques are not widely applied in industrial settings yet. And one of the major ones is the problem of safety. So in this setting, we have sort of a fundamental dilemma, because we know that we have to apply some action in order to collect information and get data and potentially explore the system. But we also know that every action can actually be safety critical and has to maintain a certain minimal operation of our system. So in industrial settings, learning from failure is usually just not an option. In addition, if we're thinking about safety, then we have to keep in mind that safety is actually not a property just of a current time instance, but we're actually requiring safety for the entire duration of a task. So we have to think about the consequences of our actions. And so, for example, if you think about this car example here, then you're currently in a position that's seemingly safe because you're still on the track. However, you can be in an orientation and with a velocity from which it's simply not possible to find a forward trajectory that keeps you on the track. So this is actually already not a safe position anymore. So if we want to think about safety, that has to mean safety at all times. And that usually requires a quite thorough understanding of the dynamical system behavior and usually some form of a model to analyze the future. So in addition to safety, there's a number of particular difficulties that we usually encounter in this domain and often don't arise in other domains of learning. This is, for one, the computation. We usually have to implement these things on an embedded platform with very limited resources. They have to be computed at rather fast rates. Then usually our controller is deployed ultimately and maintained by some operators. That has to be interpretable what it is actually doing. And then we're now learning sort of in a closed loop system and experiment. So we're not going to have huge amounts of data for each particular problem instance. And so we have to think about how we can be very efficient about leveraging that data. So I'll be mostly focusing on that challenge of safety, but we have to keep, the other components and difficulties in mind. Okay, when we want to talk about safety, we also have to define what we actually mean by that. There's, of course, different notions. What I'll be working with is a quite general one, where I say safety is defined as some safety constraint on the state, and that I represent with such a set calligraphic X. So we want constraint satisfaction for safety. And throughout the talk, I'll be sometimes a little bit more practical and pragmatic about this. Because if we think about uncertain systems, then we have to think about, the probability of being safe. And so we're going to impose that as a probability of satisfying our constraint with a certain minimum probability. So this is a quite general notion of safety, and that you can find in many applications. So for example, we've already looked at this car example where this would be the road boundary, for example, or you can think about a quadrotor flying. This could be a wall. And we can also draw this in our state space. So if we just think about a quadrotor flying up and down, we can draw this in 2D, the altitude over the velocity. So the constraints are the floor and the ceiling. But again, not all positions here are going to be safe. So actually the safe domain in which we can remain safe at all times is going to be some subdomain of that. Okay, so that definition of safety as constraint satisfaction leads us to the motivation that we'd like to make use of sort of constraint control ideas to address the problem. And here, model predictive control in particular, there is a technique that has been very successful also in practice, and that allows you to explicitly take into account constraint satisfaction. So I want to introduce that idea quickly, and I apologize to those of you who are already experts in MPC, but I just want to make sure that we're all on the same page to continue with the discussion. Let's just look at model predictive control, short MPC, and put it into perspective with the linear quadratic regulator, which is probably the most common formulation that people know, and it's also had quite success in the learning context showing, for example, various sample complexity results. So in the LQR problem, we make use of a linear dynamics model to optimize our actions to minimize some quadratic cost functional cumulative cost over the task prediction horizon. And here I'm writing down, finite horizon formulation where we usually have an additional sort of cost to go for the remainder of the horizon that we're missing. So the corresponding model predictive control formulation in the same setting looks just the same, but we now additionally impose our constraints. So our safety constraints on the states, but we can additionally impose actuator limitations, so just taking into account that any physical system will have limited actuation, which often leads to saturation issues in LQR. Okay, so for the LQR problem, we know very much a lot about the solution, and we know it has nice properties. The optimal control loss linear, and optimal value functions can be quadratic, and that can be obtained from the Riccati difference equation. And in fact, you can also consider here the infinite horizon case in a similar way by taking this to infinity and get it from the algebraic Riccati equation. Now in MPC, this is complicated by the constraints, but in this particular setting, and then if you now additionally assume that your constraints are going to be polytopes, you can similarly derive the explicit solution based on parametric programming. And you're going to find that your optimal control law is actually now piecewise affine on polyhedra. It's still continuous. And your optimal value function is going to piecewise quadratic on polyhedra, but convex. So this is actually a very nice intuition where you realize, that your solution to the constraint problem is not going to be linear anymore, but it's actually a nonlinear controller. So your closed loop system is going to be a nonlinear system. The solutions usually look very similar like this. So you have some partition over your state space, these regions over which you get your piecewise solutions. And intuitively, those regions are where different constraints are becoming active. And in the center, you would have no constraint active, and then under the same problem parameters, that would be your LQR solution. Okay, what we cannot do with model predictive control is solve the infinite horizon problem because of the constraints. Commonly, MPC is implemented in receding horizon fashion. So we just optimize over a shorter prediction horizon, and then we repeat the optimization for every sampled or estimated state. Then again, predicting forward. What's, however, very nice is that this formulation now directly extends to more general dynamics, in particular nonlinear dynamics, different cost functions, different constraints. Of course, the solution of that optimization problem that you now have to solve at every sampling time can be challenging. You can also extend this to uncertain systems, robust stochastic settings, and I'll be talking a little bit about that later. The main challenge for the theory is that you now have this receding horizon setup, and so you actually have a fundamental difference between what you're planning in this open loop forward problem here, your predicted states and inputs, and what you're getting as closed loop states and inputs. So not everything that you're nicely specifying here, not all the properties you'd directly obtain in closed loop. So luckily, people have thought about this now for decades, and especially, in the nominal and robust case, the theory is extremely well established. So we know how to write the problem. So we actually can ensure that this optimization problem is recursively feasible. So feasible at every time we're solving it. And that gives us constraint satisfaction because the constraints are specified in here. You can also show things like stability, but again, I want to focus mainly on constraint satisfaction. And usually that involves, some form of what we call a terminal constraint in addition to the cost to go, which takes into account sort of the constraints to infinity, and thereby, again, this safety property for all times forward. Okay, so there's a lot of things established about MPC, various excellent practice, a lot of theory available, but very often it can still be difficult or very time consuming to come up with the right problem formulation to really, think about which objective you need and also, come up with a dynamics model. But what I want to do is use this as a framework in order to combine it with learning and then get, safe techniques out of it. And I'll be approaching that from two different directions. First, we'll be looking at, this MPC problem as our basic policy. And then we'll use sort of learning techniques to address exactly the fact that, sometimes, the components are difficult to get. So we're going to infer those from data. And then in the second part, we'll turn that around and say we want to use some learning-based policy. And then we're only going to leverage, the constraint controller to get safety and basically augment our learning-based policy with that. Let me begin with the first part. So we've also been looking into, learning the objective, in particular looking into sort of inverse optimal control methods. But here, I just want to talk a little bit about the problem of learning the dynamics model. So we are making use of what's often called a hybrid approach here. So we leverage the fact that this is actually a physical system, that there are some, physical first principles that we can use, but then we're going to augment that with data to improve the model. So basically, what we're looking for is to learn the model error with respect to our nominal first principles model. Very often done, with regression techniques. So you could do that based on offline data, but really the much more interesting problem is to do that in closed loop, so online learning, where you directly leverage, the data that you're creating in closed loop. You're updating your model and you're feeding that back into the predictive controller. And note that this is, directly possible here because we're, formulating this as an optimization problem that's solved at every time step. There's, of course, a number of different model assumptions that you can make. You can work with what I call nominal models, for example, neural networks. But if you really want to think about constraint satisfaction, then it's important to realize that this model that you're creating, it may not necessarily be the perfect model, and there's still going to be some residual model uncertainty that you have to be aware of. And so here, there's robust techniques, often set membership techniques used for estimating, for example, bounds on that error, or stochastic models that describe sort of the distribution of that learning dynamics function. In particular, in Gaussian processes or Bayesian regression has become very popular. So this topic of your learning the dynamics model and MPC has been a focus of a lot of research over the last years. And there's a broad range of literature on these different techniques that you can find. We started by using a Gaussian process for this problem, mostly because for one, it's an extremely flexible non-parametric regression method that requires rather few assumptions, prior assumptions about the model. And if we're thinking about such a model error, then very often, we don't know a lot about this. But most importantly, because the Gaussian process gives us an analytic quantification of the model uncertainty that we'd like to take into account, while at the same time, not being, as conservative as some of the robust techniques. However, it is quite computationally expensive, and that's actually where we spend most of our time. A first important step towards that is this hybrid modeling step. So because we have our nominal dynamics model, we can now use, the Gaussian process only for parts of the model that we have a hard time of describing. So for example, think about a model. Very often you have large integrator chains, and now your Gaussian process doesn't have to live in the full state space, but it can actually live in an uncertainty subspace. Moreover, it doesn't have to be a function of all states and inputs, but only a subset of these. Okay, so the Gaussian process takes in state and input pairs and then aims at describing the modeling error between measurements that we're getting and what the nominal model describes. It's defined simply by a mean and a kernel function. The kernel describes the covariance between the data points, and that's basically our smoothness assumption on the dynamics that we have to specify. And then once we see data, we can condition on that, and we get our posterior distribution. So here, the nice thing is that we're not only getting a mean estimate of that function, but we can represent also the residual model uncertainty directly. Okay, now we want to put that into our optimization problem. in order to leverage that improved model, but also, use that model uncertainty in order to be cautious with respect to the constraints. So we put that into our problem formulation, and because that's a distribution that makes it a stochastic problem, we formulate our constraints as probabilistic or chance constraints. Often we minimize the expected value of our cost function. But it's still not tractable in this form. And so you have to go through various approximation steps. The first one is that you have to think about how to propagate your dynamics forward, because if you propagate, a Gaussian process through, nonlinear dynamics, then these are non-Gaussian. Nevertheless, sort of a common approximation is that you do treat every function evaluation as independent and approximate every step as Gaussian. There's different complexity accuracy trade-offs you can take here, but there's also more recent results on how you really take sort of the correlation between function evaluations into account. And then you similarly approximate your chance constraints, and you arrive at a formulation that's written, in form of your mean and variance dynamics. So that's quite nice, but it's still a large problem, a lot of variables, nonlinear. So if you want to compute that quickly, we have to think a little bit harder. And so what we do here is we leverage that, in MPC, we're actually resolving that problem at every time step. And so this gives us some notion of where we are with our planned trajectory. And we can use that to construct a local sparse Gaussian process model that's a lot cheaper. And then in addition, we also leverage, the different nonlinear MPC solvers that are available in order to get the computation times really down. I just want to show you one particular implementation that we've done together with AMZ, as our student racing team, so putting this on an autonomous race car. So here you can see that we start with some conservative tuned controller. And again, you have to run your system in order to get data in the first place. And here, this is the intuition of the nominal model, that this should be just enough to get you off sort of the ground and start collecting data. Then you enable your learned model, and you see that, by improving the model, your lap times go down. I'm now going to show you sort of the 8th lab, where you see that we're racing much faster. The green dots are sort of the data points, and those are sort of collected on the fly. We're selecting them according to, their information. And you also see, the prediction in gray. And so we're learning, however, while, being cautious with respect to the constraints. And again, that's really important. So here you see a snapshot of the video. Where you see your prediction getting a lot wider because in that curve, we actually had a lot of model uncertainty, and that's, again, an important part. Okay, so I think that example, but also, other implementations in our group and other groups show that there's a lot of performance to be gained with these techniques. But there are also a number of challenges, and one is, for example, that the theory is quite challenging, and it lags sort of behind what we're already seeing in the performance. That's for one, of course, due to the fact that we need to do all these approximations, but we also just have a fundamentally difficult nonlinear stochastic MPC problem. So there's been some results on, analyzing input to state stability of these problems, or deriving bounds on estimation errors, if you can take certain boundedness assumptions. Now, however, if you really want to go for, the unbounded distribution, then what we did is just, step back a little and looked at stochastic MPC theory again, starting, from a linear dynamics model. And we realized that, some of the properties that we want were even not there for this setup. And we've now sort of come up with a modified number of modified formulations that directly give us sort of closed loop chance constraint satisfaction, so basically safety, and recursive feasibility. And I'll talk a little bit about how these techniques work in the second part of the talk. The other challenge is related to active learning. Most implementations learn passively, so they just take whatever data is generated by the closed loop system and then learn from it. However, for many applications, it could be very important to also think about which information we should actually be collecting to maximize the performance in the long term. That's the classic problem of dual control. It's already been looked at by Feldbaum in the 1960s. There's a more accessible review paper by Ali Mesbah that I would recommend looking at. We've recently looked a little bit into that and proposed, an approximate dual stochastic MPC formulation that sort of derives things from a stochastic dynamic programming framework. So this is really if you want to do online active learning. If you're in an episodic setting where you can repeat a task, then you can also leverage, Bayesian optimization techniques that systematically trade off exploration and exploitation. And there's also a number of very interesting research going on in this direction. Okay, so why shouldn't we always be doing this and sort of build on an MPC policy? And we've now looked into learning the model, but a lot of the difficulty is also related to the objective. So you have to be able to express what you want to achieve with your task as mathematical function of your states and inputs. Moreover, that function usually has to have certain properties related to the controller, but also it has to be differentiable, sometimes even convex. And if you think about a very abstract task as saying open the door, we cannot just simply have a 0 or 1 reward in that setting. And often, the complex tasks require a very long horizon, and that significantly increases the computational complexity of this. And of course, as I just discussed, this exploration problem, the dual MPC, is very hard in this setting. And that motivates why, you could think about just taking a more general, for example, reinforcement learning policy as your performance controller. And then in the second part, I'd like to talk about how we can use just the core of MPC, and this is constraint satisfaction, to augment this now with safety properties. But before I go into that second part, let me pause here for a second and see if there are already questions to this first part of the talk.
Yes, so if anyone have any questions, feel free to post in the chat or raise your hand to directly interact with our speaker. So actually, Melanie, I got a question. Since in your learning for MPC work, you need to collect data online and also update your model. So how often are you doing that? Are you updating your model every time step? That can be quite time consuming, right?
Yes, so actually that's what we did in this race car example. We did update the model at every time step. And this is really why, everything had to run in 20 milliseconds, which is very fast. And that's why, we really had to think about how to approximate the Gaussian process to get that to work. But at the same time, it's you could probably also run it at a slower rate, but then you have to be careful also that there's no bigger jumps, when your model changes a lot in your behavior, which is why we wanted to do that continuously.
I see, cool. And also there another question in the chat. So Joe asked about, is the learning MPC mainly for trajectory tracking or motion planning?
Yeah, you can use it actually for both. Set point regulation, trajectory tracking is the classical setting. You can also use it for motion planning. Of course, if your constraints are becoming, non-convex, then very often you need sort of a higher level decision strategy that basically first decides which strategy you're going to follow, and then you can apply MPC based on that.
Okay, thanks. And another question is, Christine is asking, how do you optimize the Gaussian kernel hyperparameters?
So we use really the standard tools here. So we didn't look into that particularly. So for right, so that's important to clarify. So for the really fast timescales, we actually keep the hyperparameters fixed then for the online part, and only use the upcoming new data to evaluate the GP, but we don't re-optimize the hyperparameters. Basically, that's based on the intuition that your fundamental dynamics properties, so your smoothness properties, are not going to change, and therefore we don't re-optimize.
Thanks. And yeah, a follow-up question is, have you tried variational methods to make your inference faster?
We haven't tried that so far. No, there's actually, I agree, there's a lot of new things that we could try and compare.
Cool, thanks. Yeah, and I guess there are other questions for now, and we'll let you know like if we got more questions.
Great. So then I'll continue with the second part. So here, what we want to do is really think about a rather general framework that we call a safety filter that can be combined with sort of any learning policy to make it safe. And so we're going to be agnostic with respect to which particular policy we're implementing. And the way we do that is by just looking at which proposed input we have, from the learning policy. And then we analyze if that's going to keep us safe for all times forward. If that's the case, then fine, we can apply that input. If that's not the case and we cannot, that test fails, then we have to provide a suitable modification that keeps us safe forward. So this is the main idea, and more abstractly, you can think of this as some safe domain within your constraints, in which some controller that at least keeps you safe. Now, the challenge is often in how you compute such a safe set. And so let's have a look at what exactly we need. So we need to verify if our control input is safe, and then we need to modify it. And quite basically, you can think of such a scheme as I said, some safety controller with slow performance. It gives you safe operation. And then based on such a safety controller, compute your safe set as an invariant set of states. So invariant means that you can remain in that set for all times under the applied controller. And if you then fit that into your constraints, then you're always safe because you're never going to leave your constraints. So for a continuous time system, your strategy can then just be as simple as applying your learning input while you're inside of your safe set, and then applying your safety controller on the boundary when you would be about breaching your safety. But again, computation of these components is hard. Moreover, you want to be able to improve them as you're seeing more data. So there's been a number of directions how people have looked at the computation of these components. I think historically, probably first in the form of control barrier functions, building on sort of control diaphanous functions. There's a lot of active research going on in this direction, but often they're still difficult to compute for many constraints. There's the direction looking at sort of reachability analysis to compute the largest invariant set. Also a lot of nice research going on, but very often the techniques are computationally quite expensive. We've looked a little bit into approximating these based on convex optimization methods, but that often ends up being very conservative. Now, this is just in the framework that I've described before, but there's of course a lot of related work just looking more generally at safe RL or RL with temporal logic constraints. Okay, so now looking at the limitations of these methods, what we realized is that what's hard is that we were trying to compute these components explicitly. And thinking about how to avoid that led us to the idea that actually with MPC, mod predictive control, we can approximate our maximal control invariant set. And so the idea is going to be exactly that. We still make use of some safe set, but this can now be rather small, some small neighborhood of our target. And we can now also certify points beyond that by just checking if we can actually find a trajectory that's within our safety constraints and leads us to the safe set as a terminal set, because from then on, we know some controller that works. So verifying if some input is safe means verifying if after applying that, I get to a safe state from which such a trajectory exists. Why does it work recursively? Well, if you afterwards, for example, proposed an input that's unsafe, so you can't find such a trajectory, then you could just follow the one that you have computed before. Now, however, we do have to solve, this planning problem anyways to figure out if we're safe. So what we can do is we also optimize over this first input. We basically directly optimize over the entire trajectory such that all constraints are satisfied and we end up in the safe set. And then what we'd like to do is ideally make that first input equal to the learning input. So we're going to minimize the deviation in some sense. And if our learning input is now safe, then the optimal solution to that problem is going to be the learning input. If it's not safe, then it's going to give us the closest in that measure safe input. The nice thing about this is that we've now reformulated our safety certificate by solving this finite time constrained control problem. And we can show that the feasible set of that problem is, again, a safe set. The advantage is that we're never explicitly computing that safe set. It's implicit. We also have an implicit safety controller. This problem directly is an implicit decision module, checking if it's safe or needs to be modified, and also directly provides the modification. And we can now make use of this entire backend of solvers that's available for these problems. Okay, so just to step back for a second. So what we've done here is basically we've tried to separate performance from the safety requirements. So the learning policy is just focusing on performance. And we have another module that just looks at verifying if that's going to be safe. And that's often advantageous because the learning policy is not affected or limited all the time by verifying safety and being robust, for example. At the same time, this prediction problem is often, you can find a forward trajectory with a shorter horizon that's safe, while it would be really hard to formulate your entire performance problem in that framework for all the reasons that we discussed before, right? But here we really bring it down to just leveraging this constraint satisfaction part. Okay, so it's a very nice and modular setup. The challenge is, of course, that we need some model to do this forward propagation. You could just use your nominal MPC controller, and that would work for many applications. But we've spent now a lot of time just thinking about different uncertainty formulations to make that theory rigorous, starting from linear systems with additive banded noise, stochastic noise, nonlinear systems, also distributed systems and networks of systems. And I want to talk about the stochastic part and the nonlinear part, as I think there's a few very nice ideas that I'd like to share with you, even though I won't have time to go very much into the detail. For all of these methods, what we're doing is we're building up on sort of a robust idea. So in robust MPC, what we do is we start with sort of some nominal model description, and we have some error, and that error is bounded in some set that you could, for example, estimate from data. And then a simple scheme is that you basically use your nominal trajectory for planning forward, and then you apply a tracking controller on the uncertain system such that it stays close to the nominal one. So reduce your planning to the nominal dynamics. And here I'm going to use the variable z to distinguish now the nominal system from the uncertain one. And then in order to take care of safety or constraints, you tighten your constraints on the nominal system so that your constraints on the uncertain system also work. And you do the same with your terminal safe set. Okay, so that's just the intuition on which we will be building. And now I want to talk about two particular problem settings. In the first setting, we take a general system description, potentially nonlinear system with a parameter that we don't know. So we just assume some prior distribution of that parameter. And then we have some additive process noise that can be unbounded, for example, just a normal Gaussian assumption. In the setting, our goal is that we'd like to satisfy our constraints and probability. Here, I'm just taking the same probability for simplicity. You could also take a different one for states and inputs. And then in order to write down the problem, we're going to model that system slightly more simpler by taking, a linear nominal system approximation here, and then describing, the deviation to the real system by some additive uncertainty term. And that we're going to derive a bound on that such that, the bound holds with a certain probability p theta for all states and inputs. And now note that the idea is, of course, that you're going to improve that nominal system description and the bound as you're collecting more data. So you're also learning the dynamics model here. Okay, because that bound has to hold for all states and inputs, I'm going to simplify the notation a bit and just, assume that's a function of time. All right, so if you now write your filter planning problem for this, then you would write down your dynamics as we just derived them and your chance constraints. And you have the same objectives that we looked at before, minimizing the deviation to your proposed learning input. Now, commonly in a stochastic MPC formulation, the constraints are imposed for each prediction, so conditioning on the current state. That's actually a little bit more restrictive than what we originally wanted. We want closed loop chance constraints, and it would actually be sufficient for that to condition that on the very first initial state. So, and that actually helps us now to formulate that quite efficiently. The idea is, again, that we're using such a tightening approach, but now we have a stochastic system that we have to propagate forward. And for this, we're going to use the notion of a probabilistic reachable set to do the tightening. And I just want to say quickly, what the idea about this is. So you have your nominal linear system, and now we have a tracking controller that keeps our uncertain system close to the nominal one. And here we can just choose in the setting a linear controller. Which leads us to an error system between the two that's driven, by this closed loop dynamics, and we have the two uncertainties here. In this setting, the nice thing is that we can split the parametric error from the stochastic error, and there are two systems that separately evolve. So for the parametric error, we can robustly address that. We're going to compute a robust positively invariant set, meaning it's a set in which our error stays for all times. And because our bound was designed so it holds with probability p theta, that's going to be a robust positively invariant set with the same probability. Now for the stochastic error, we're going to compute a probabilistic reachable set. And what that means is if we start with zero error, because at the very beginning, nominal and uncertain system are the same, then what we want is that our error remains in that set with some probability p for all times. So you can think of this as, start thinking about, a one-step, two-step, three-step reachable set. So if these are our error dynamics, one step, two steps, three steps, then, after one step, we can derive such a reachable set after two steps, three steps. And so this is just, the infinite horizon version of that. Okay, now the nice thing in the setting is we can compute these sets separately. Then we get one overall probabilistic reachable set out of the Minkowski sum of these that hold with the combined probability. And we can now use that to tighten our constraints. So we arrive at a similar simple formulation based on the nominal system dynamics with tightened constraints. But note that now, we're relying on this tracking feedback controller. So also our first input has to be represented in that form. Now, in standard stochastic MPC, you would initialize your nominal system at the uncertain system, but that can, of course, lead to difficulties in your constraint satisfaction because that's potentially, has unbounded noise. And it also leads to loss of our nice closed loop guarantees because actually here our error analysis was based on the fact that we had this linear error evolution. And if we're resetting our nominal system, that's not going to be maintained. So what we do instead is we actually initialize our nominal system with the prediction from the previous time step. And that has the nice advantage that this theory directly goes through. Now we do still get feedback from our actual state in the objective basically by looking at using that feedback controller. And that's actually a setting that you can also do for general stochastic MPCs, what I referred to at the beginning. where feedback would similarly come into the cost. And from that formulation, we nicely get sort of closed loop safety and closed loop constraint satisfaction directly under that controller. And moreover, note that you can now, iteratively improve your terminal set. When you see more safe states, you can enlarge that. You can potentially start with an extremely small set, just a point. Okay, so it's a very nice framework if you have such a problem setting. But what we found is that it can be limiting for very nonlinear systems because we have to take this linear system assumption. Moreover, we were bounding our model error globally, and that can also be quite conservative. So what we wanted to do is think about sort of a nonlinear extension of that problem. And here, we start with a very similar problem formulation. Again, we have a parameter that we don't know, so we have some prior distribution, and now we have some additive uncertainty, but we're going to assume that this is bounded now. So we're staying more in the robust sense. And as a result, we also formulate our goal slightly differently. So we want to maintain, constraint satisfaction for all times with some probability. And we call that it's robust in probability. It's basically, if you get your parameter right, then you're going to be robust. In order to apply, robust ideas, we again, formulate this in terms of a nominal system with some nominal parameter estimate, and then, bound the error to this problem in some error set, so that the error set again holds with our desired probability of being safe. Okay, so now for this problem setting, we need some nonlinear robust technique. And here we've opted for one that I still find extremely nice because it's so simple to implement. And basically the constraint tightening is here just done based on a scaling along the prediction horizon. And that scaling is related to your contraction rate of your tracking controller. So basically how well you can compensate for uncertainties up to a certain amount. And then you use that to do the constraint tightening. So I'm not going to say much more about it, but if you look for a very nice nonlinear robust MPC method, then I recommend you to look at that. Okay, so what we rather want to focus on in the remaining part of the talk is that just applying robust MPC in that setting that we had can become prohibitively conservative because we think of this as a learning problem, and at the beginning we've potentially only collected data in a small domain of our state space, and if we do what's commonly done in robust MPC and takes in a uniform error bound everywhere, that can be quite bad. And sort of if you think about the easiest example of taking just a linear parametric model and you draw samples from your posterior parameter distribution, then you see that you're going to have sort of low prediction uncertainty in some parts and high prediction uncertainty in other parts of your one-dimensional state space. Okay, and similarly, of course, if you do that in 2 dimensions, what we want to avoid is that we take this high prediction uncertainty everywhere. Instead, what we'd like to do is to turn that basically around and say, well, we're going to first decide on a model error that we're willing to tolerate. And then we're going to restrict our planning problem such that that model assumption is valid. So we can't directly impose that the error lies in some maximum error set. We could try to compute that subset in which the model error is valid, but that's often expensive and you have to recompute it if you collect more data. And so we were going for an implicit description of that. And the way you can do it, you don't know the error, but what you can do is bound your error as a state and input dependent error bound. So for example, you can sort of define a confidence set of your parameter and then sort of define bound the error that you're going to get for all parameters in that confidence bound. And then we can impose that this set actually has to be a subset of our maximum tolerated error. And this we can now directly impose back into our planning problem. So saying, okay, we're now for analyzing safety. We're looking for a trajectory. We're using the nominal system, tighten our constraints, and we have to make sure that when we're planning, we're not going anywhere where this model assumption that we use for the tightening is not valid. If you stick to the Bayesian regression setting and normal Gaussian distributions, then that constraint actually reduces to a very simple constraint on your variance. Okay, so the nice thing is that we can really now reduce the conservatism of that robust MPC formulation. We have to assume that error bound is Lipschitz continuous. But if we do that, then we can always select the constraint tightening first, and that corresponds to some model error that we're tolerating, such that if we're initially feasible, that implies in a safe system operation, meaning that our closed loop system satisfies all our constraints with our desired probability. Okay, and rather than going more into the theoretical detail, I want to show you a couple of examples. So here we're looking at the classical example of a pendulum. We're looking at a swing up task from downward hanging to upward position. We have constraints, so we can't swing over and we can swing back a lot to gain energy. Here you see, the model that we're learning as we're collecting more information. And here, this is the confidence of our current model. So as we run it, you see at the beginning, we only have a bit of data close to the downward hanging position. So our confidence is not high enough to really move upwards. We're always moving so that we can find a trajectory backwards to our safe domain hanging downwards. And as we go now through these episodes of learning a bang controller, we are able to complete that task without ever violating the constraints. I know that this is actually a really difficult problem for most settings. You can also do that for slightly more exciting applications. So here we've implemented this for a small race car. We have a human learner, which is actually not trying to do a good job, but it's challenging our safety filter. And that manages, to keep the car on the track at all times. And here you can see how, it does this safe forward planning. Or you could use sort of a learned policy here. We take a neural network that learns from an expert. At the beginning, it doesn't have a lot of data. And so our safety filter has to intervene quite frequently to keep the car on track. But then the more data is collected, then really the filter intervenes less. And that shows that we can now really learn safely, in closed loop with that learning policy. Okay, with that, I'd like to summarize quickly before going into asking for more questions. So I think there's a huge opportunity in, combining learning and control. But the safety concerns, I think, are really a limiting factor right now. And what I've talked about is taking sort of constraint control, and in particular MPC, as a framework. We first looked at, integrating learning-based components and dynamics models, for example, into MPC to get better closed-loop performance. Particularly, we looked at Gaussian processes, where you get really nice high performance, but also a cautious controller. Now, in the second part of the talk, I talked about this new idea of a modular approach, how you can wrap basically safety around any other learning policy. It's a nice and scalable implicit formulation. We've looked at different problem settings. If we have, stochastic unbounded noise or nonlinear systems. And key is really to not make this too conservative. So you're not restricting performance too much. And for this, we were looking at this planning and confidence subsets approach. Before I, go into questions and forget to mention it, I just want to say that, there is this nice conference on learning for dynamics and control that we started a couple of years back. It's going to happen hopefully at ETH Zurich next year. I hope you have, the deadline on Friday in your calendars. And I definitely hope that I'll be able to see you next year in Zurich. And with that, I'd like to thank again, the people that have been working on these topics, as well as our funding agencies. And I'll now have time to ask for questions. And I thank you very much for your attention.
Thanks so much, Melanie. This is very exciting. And we got a couple of questions on the chat box. I would like to ask the participants if you would like to unmute yourself and ask. So Joe, would you like to talk with our speaker directly? Or yeah, I could. Yeah, so he's asking, how do you select the weights for the MPC cost function? Is it trial and error needed, or like is more a principled method?
Right, so I guess I'm not entirely sure which part that refers to. So in general, when you tune your MPC cost, yeah, that's often trial and error, but you can also do that in a more systematic way. And for example, here we've also, and other people have looked at Bayesian optimization techniques to tune the weightings for your MPC costs. We've recently started to do that, for example, for the race cars. And so that you really find the parameters that give you the best closed loop performance.
Yeah, and Ying is asking, do you update the safe terminal sets during the learning of the system?
Yes, absolutely. That's quite important. So for example, for the stochastic, but also for the other part, you often start with a very simple, terminal set that can be just, a target point that is safe. And then as you see more safe states, you start enlarging that. That's also very related to, what Francesco Borelli is doing in this, in these repetitive learning settings. That really you leverage every round of data that you're getting to improve that problem setting and make it less and less conservative. I think for the example of the pendulum that I showed there, we didn't do it, but for the others, yes.
Okay, cool. And Rafael is asking a question regarding the first part, learning inside MPC. So how do you estimate your current state? So are you using any like extended common filter or moving horizon estimate or something else?
Yes, for sure. So the estimation problem is one that we always nicely exclude. But yes, we usually make use of actually the extended Kalman filter. We're currently looking into moving horizon estimation as well for this. But for all the examples that I've shown, these are traditional extended Kalman filters.
Okay, yeah,
Yeah, Melanie, I have a question. Thanks for the great talk. So regarding the second part, if I understand correctly, the filter works like in a post-learning way, like you first learn some fancy policy first from reinforced learning or imitation learning, whatever, and then you apply the filter. So my question is, are you interested in like a learning, like a filter during the learning? During the learning process, you kind of teach the learner, like you should follow this safety manner or something like that.
Absolutely. No, actually it was meant in the sense that you apply this during learning, because especially, at the beginning, when you start rolling out your policy and you have not seen a lot of data, that's going to be the part where it's unsafe. And this is where you want to use your safety filter to prevent any unsafe actions. But you're raising a very important point that actually, you have to inform your learning policy of those safety actions. And so there's some very nice things that you can do. You can integrate, a cost on, the deviation of your actions. So you get sort of a penalty on whenever you're overwriting your action. And actually, thinking about, the MPC properties, you can show that all of this remains continuous. So it actually, doesn't affect, the properties of your learning problem in a negative way. But yeah, there's a lot of additional work, that can and has to be done on that side.
Yeah. Thanks.
Cool. And maybe let's take the last two questions. So one is, so in which aspect are the learning MPC different and similar to the iterative learning control?
So in MPC, you're not necessarily running this in an episodic setting. So you can also run this, in an online setting. I think that's number one, how this is not necessarily the same. If you look at it as in an episodic setting, your repetitive learning, then you can clearly, look at it and see parallels to iterative learning control, especially if you look at iterative learning control that makes use of optimization as well. And so, all of these things are, of course, are quite related in their, in their fundamental source or origin of the problem.
Thanks. And the final question is you have demonstrated very cool applications on the racing cars or the pendulums. So Amara is asking, how many computational resources do you need in these cases in order to run these different types of algorithms?
Very much depends on the scale of your problem and the dimension basically of your state space. So as I said, very often, these have to be brought down to embedded platforms. For the little race cars, you can often, play a trick where, we have a radio link, so they don't necessarily have to compute on board. So I think that very much varies, but you can actually, that's quite nice. There are now embedded, MPC solvers for pretty much any embedded platform that are already available, and where you can sort of then generate your code for some particular computation platform.
Okay, cool. Yeah, I guess that's all the questions. Thanks so much. So with all this, we'd like to conclude today's seminar. So let's thank our speaker again for this very interesting and very informative talk. So next week, we're going to have Professor Claire Tomlin from Berkeley, and it will be next Wednesday at the same time, 9 a.m. So hope to see you all next time. Yeah. Thanks, Melanie.
Thank you so much again, everybody, for attending and listening.
Okay, cool. So we're going to post the video later, and if you have any questions, feel free to maybe reach out.
Of course.